Hello, today we will be solving this problem called grid paths. There are 88,418 paths in a 7 by 7 grid from the upper left square to the lower left square. Each path corresponds to a 88 character description consisting of characters down, up, left, and right. For example, the path from here to here corresponds to this sequence. So first we go down, then right, then up, then right, and so on. So our task is that we are given a description of a path which may also contains characters question mark, which means any direction. So our task is to calculate the number of paths that match the description. This is our sample input. So our first move can be anything. Our only constraints are at these positions, and this means that after the first 6 moves we will have to move right no matter what, and in this case there are 201 possible paths. So let's try to explore this example. I'll just take this prefix and try to make sense of it. So this is the prefix, and at the beginning we are at position 0, 0. And what I will do here is that I will perform a DFS, and this is a depth first search. This means that at each position I will see the possible moves that I can make, and I will just perform the first one. Then I will continue from there. After that I will see my moves, and then I will choose the first one again and keep exploring my choices in that way until I get to the end, or until I cannot move a possible to a valid state. And at that time I would have to backtrack all the way down to the last valid choice I could make, and then I will explore it again. So, and my choices are up and down and right and left, and I will just choose to perform them in this way. Okay, so my first move here is up, so I'll try to go up, and this would mean I'll have to go to -1, 0, and that's not possible. So this is not a possible move, so I'll just go back to the last valid state. Then my second move is going down. So if I go down, I'll go to position 1, 0, and I will continue from here. Again, I can make any move, so let's choose to move up. So if I move up, I'll go back to position 0, 0, but I cannot visit the same position twice. That's why this is not valid as well. But this gives us an idea that we have to remember visited cells or visited square. Okay, so if we visit a square that is already visited, we just stop. And here, since our grid is small, we could just have an array of like vis 7, 7. Okay, let's move on. Now my second possible move is going down, so I'll go down again to 2, 0, and I will do this again. So going up would take me to 1, 0, so that's not possible. Then I will go to 3, 0, and I will continue. So this would take me to 2, 0 again if I go up, but that's not valid, so I'll go the other way to 4, 0. And same thing here again, up is not valid because it's already visited. I'll go down to 5, 0, and here again I'll go up, but that's not valid, so I'll go down to 6, 0. And at this position here I have to make a right move. I don't have 4 choices here, so I have to make a right move, and this will take me to 6, 1. And I'll just carry on here until I get to the end, or until I cannot make a move. So if I cannot make a move, so if x, like in this case, I'll just return 0, or like increment the number of the count of good paths by 0, so plus 0, something like that. And if I get to the end, so if pause equals 48, if I am at the last position, then I would have to check if I reached the correct cell. So if I am at position 60, and one other thing to notice here, if I get to position 60 before the last move, if I get to 60 and it's not my last move, then I will have to return 0 as well. So I will have to stop if x equals 6 and y equals 0 and pause is different from 48. So these are some very rudimentary conditions that we came up with so far. So I should not visit the same square twice, and as I said here, so I also should stop if I get to the lower left square before the last position, and of course I should not go out of the grid. So with this basic condition, let's visualize these paths in the actual graph and see what happens. So here is our grid. We are at the upper left corner and we have to go to the lower left corner. So as we said, our first move was to go up, but it would be out of the grid. So instead we have to go down, then we'll try to go up, but it's already visited. So we'll keep moving down until we get to our lower left corner. But as we said, since we reached the last position and it is not our last move, then this would not count and we would have to backtrack. So we'll backtrack to the last valid position, and now we'll have to go right and up, 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 then we'll try to go down, then right, then we'll try to go up again, and so on. But notice what happens here. The cells that we have not visited so far were just one component, but now they became two components. We have a block here and another block here that is not visited. And if we go in this direction, we would not be able to visit these cells without self-crossing. And the same would happen in this block. So if we visit these cells, we cannot visit these. So this you should get the same feeling in this condition, like the one you would get in a snake game when you know that you are just doomed. So now, since our approach is very naive, we'll just keep on exploring, but we know that our next improvement would be to fix that. So as we saw in the animation, things turned out ugly when we got to this state. So basically we were at this position, then we moved down. So we visited this square and we are now at this position. And since we splitted the unvisited squares into two blocks, then we lost, because if we visit these blocks, we're not gonna be able to visit these blocks. So basically this is a losing state. But how can we encode for it? So at this position, let's look at the cells adjacent to it in all directions. So the cell to its left is not visited, so it's unvisited, and the cell to its right is not visited as well, and the cell up is visited, and the cell down is out of the grid. So if you cannot go up and down and you have to go left and right, then you are doomed. So we have to encode for this in this way. So basically at each position we have to check these four directions and if we have this configuration, then we will just stop. And this doesn't have to be out of bound like in this case. It could be something like this. We could be at this square and then we will move to this square. So at this position we have something that is similar to this, but instead of having a move that is not permissible because it is out of the grid, it cannot be permissible because it is just visited. So in this case, our left and right are the cells that are visited, while the cell up and down are unvisited. So if we have this pairing, then we would have to stop here again. We cannot visit both blocks. And lastly, we have this other configuration that's an invalid state. So if we are here, for example, and we move here, so if we are at this position now, then left and right are unvisited and up and down are visited. And here again we will have to stop. So these are new constraints that we will apply to our algorithm and see what would happen. So now let's see what the animation looks like when we added those new constraints. So here again it chooses to go up first, and if you can't, you will just go down. And again you will reach the last square beforehand, so it is not accepted as a valid path. And as before, it moves right, then up, then now it moves down. And let's see if it's gonna create additional connected components. It does not, so it detected that and it will just continue. So that's great. Now we're gonna have our first valid path. See how fast we got to our first valid path with simply adding those few conditions? Now it's gonna backtrack and try to find another path. And this would be our second valid path. But notice what is about to happen here. See, even with our conditions, we still created two blocks here and here. But why did that happen? So what we encoded does not check for this. Look what happened here. We were at this position and we chose to move right. So before we created connected components to the right and the left of our actual position, or up and down, but in this case we created new components here up and here to the left. And this happened because we had this special configuration when we were at this position and the cell that is up and to the left from us was already visited. So this is another kind of junction we created here. The other junctions were by adjacency, like by side, but here it is by corner. So we have to check for these two. As we saw in the animation, we have to take care of adjacency by corners, and we have 4 cases, and these correspond of course to the 4 corners of our actual position. So if we are at this position and the cell to the left and up from us is visited, and the cell up from us is not visited, and the cell to the left is not visited, then we just created 2 components, and that's bad. So from these 4 cases arise 4 new conditions that are the following. So if we are at position xy and the cell at position x minus 1, y minus 1 is already visited, and up and left are not visited, then we would have to stop. And the same thing would apply for the 3 other cases. Now let's add these 4 additional conditions to our algorithm and see what would that look like in animation. So let's see what our new conditions change now. So as before, it's gonna start going down, go to the lower left cell and get a wrong path. Then it's gonna continue in the right direction for now. It's gonna find the first valid path. Backtracking now. The second valid path. See if it does the same issue as before. Apparently no, it does not create gaps. The third valid path. See how it stopped before creating a gap? And here again. A new valid path. See how it stopped again there? Another valid path. So before moving on to the code, let's just sum up what we said we were gonna do. So we said that we would remember if we visited some square, and we're gonna do that with an array of booleans of size 7 by 7. Second, we said if we reach the lower left corner and we are not at the last position of our string, then we would stop. Then we will check for adjacency by side, and we said that would happen if left and right are either visited or out of the grid, and up and down are both unvisited, or if left and right are both unvisited and up and down are either visited or out of the grid. And lastly, we were gonna check for adjacency by corner, and these will take care of the 4 cases. And we doing this, we're still gonna use DFS, but we're gonna prune bad paths or bad possibilities. So these are our pruning criteria. So if going from here on will not lead to a valid solution, so we'll just not visit all these possibilities, and that will help us reduce the search space. And we're gonna go from 4 to the 48 possibilities. That was like astronomical, and will take more than the age of the universe to go through all those possibilities to a solution that will run under a second. So that's amazing. So let's check out the code. This is our program. To make things clear, I'll just make a define here, and this is to check if my position is valid, because as we said we will have to check if moving to a certain position will be out of the grid. So this checks if A is greater than or equal to B and A is less than B, then it would return true, otherwise it would return false. And also I'm gonna use these array of ints to encode the 4 possible moves. So the first one will encode the move for moving to the right, and the second one would be encode the move for moving to the left, and then that would be moving down and up. And I would also declare a macro for this, so right is 0 and so on. Also, since I would need to read the position of the character at each position of my string, I will declare it as a global variable, and I will also declare my array of int here, or I could also use booleans to keep track of which states of which cells have been visited. So I'll start by reading my string, and then I will call my count path function, which is gonna be a recursive function that's gonna mimic the behavior of DFS. So I start from position 0, 0, as we saw in our graph. We're gonna start from this position, and at this point the character we are pointing out is 0. And then I'll just write my count paths function. It returns an int that counts the number of paths, and an int is enough. As we saw, there are only 18,000 paths. And then this is my breaking condition. So if I reach the last position of the string, then I don't need to go any further. And here I will have to check if I reach the lower left corner or not, and this will return true if I did and false otherwise. Then if I reach the lower left corner and I am not at the last position, then I'll just return 0. So this takes care of our first check. Then if the cell is already visited, then I'll just return, and this checks for visited. Then I'll declare a vector of boolean of size 4, and this will help me calculate the number of like for each cell in 4 directions whether or not I have visited it. So as we saw here, I need to check for visited for left, right, up and down. And I'm gonna loop through my 4 values here. So for k equals 0, k less than 4k plus plus, I will use my dx and dy arrays here to move through all possible directions, and I will use my define is valid here to check if a position is valid. So if is valid x plus dxk, that means I can move to that cell. Then I will just note that visited would be equal to the value of vis, and I will move on. So if this encodes for the first condition here, if left, if not visited down and not visited up and visited right and visited left, then I will just return 0, and I will do the same for the other direction, and this takes care of adjacency by side. Then I will move on to adjacency by corner. So this first checks that the cell x minus 1 y plus 1 is valid, and then it checks that it is visited, and this corresponds to x minus 1 y plus 1 this, and then it would check that up and right are not visited, and then if up and right are not visited, then I'll just return 0, and I'll do the same thing for all 4 corners. And now, after all these checks, I will just mark this cell as visited, and then I will read the character I am at to see the moves that I can make. So if the character I am at is an interrogation mark, this means that I will move in 4 directions, and to do that I'll just use my for loop with my dx and dy arrays. So for k equals 0, k less than 4, I will check the cells I am going to are valid, and if they are valid, I'll just add what my recursive function will return to the actual number of paths. And else, if for example the character at position is right and y plus 1 is less than 7, meaning that I can move right, then I'll just call my recursive function and add it to the number of paths. And I will do the same thing for left, up and down. And at the end, I'll just undo my visited here, because I might need to visit it again through some other paths. So after I do something, I have to undo it, and that's the principle of backtracking. And at the end, I'll just return the number of paths I found. So that's pretty much it. Let's go ahead and submit. So that worked. Thank you for watching. See you in the next video. Bye bye.